In this video, I just want to review a couple of properties of integrals and then talk about finding area between curves. So this first problem, you see an integral from 0 to 3, an integral from 0 to 2, and then it asks us for an integral from 3 to 2. Now, think about this in terms of area, because that's what an integral finds, is the area between the curve and the x-axis. So this is saying, the area from 0 to 3 is 6. There's 6 units of area. And the area from 0 to 2 is 4 units. So there's 4 units of area from 0 to 2, but there are 6 total units from 0 to 3. What I can conclude from that is that the area from 2 to 3 must be those additional 2 units of area, right? If there are 4 units of area from 2 to 3, I must have added 2 more units between 2 and 3 to get to 6. You'll see that this particular question asks us, okay, well, how about from 3 to 2? Well, when you reverse your bounds, you change the sign. So the bounds being changed like this instead mean the answer is -2. And remember that property from integrals, that when we change the signs, because we usually like to go from smallest to biggest, and we are allowed to do that. We're allowed to change signs. We just have to we're allowed to change the bounds as long as we change the signs. Okay. Next, if f of x is equal to the integral from 2 to x of t cubed minus 1 dt, then what's f prime of 2? So essentially it's asking us to take the derivative of both sides. So if I take the derivative of f, I get f prime. If I do the derivative of an integral, I get the function out with some small changes. Okay, so I'm going to multiply this by 1. I'll explain here why in a second, because obviously multiplying by 1 doesn't really change anything. But it's good to remember. The derivative of an integral spits back out the original integrand with the bound substituted in. But we also then have to multiply by the derivative of the bound. And that is part of Fundamental Theorem of Calculus Part 1. And it has to do with chain rule. So, for example, if the bound weren't x, if it were x cubed, then I would multiply here by 3x squared. And I'd put x cubed cubed. I'd put x cubed in place of t, and then multiply by the derivative. If instead it were something like, the sine of x, then I would put sine in place. So I'd have sine cubed minus 1, and then I multiply by the derivative of sine, which would be cosine. So it's just something to be careful of and remember. It, of course, doesn't really make a difference here because the derivative of x is 1. Now we plug in 2. So f prime of 2 is square root of 2 cubed minus 1. So the square root of 7 is our answer. Okay. Next, if the integral from 1 to 4 of f of x is 7, then what's the integral from 1 to 4 of 2 times f of x plus 5? Well, we're going to use some integral properties here to split this thing up into kind of manageable pieces. Integrals can be split over addition and subtraction. And what I mean by split is I can write this as the integral from 1 to 4 of 2f of x dx plus the integral from 1 to 4 of 5. Okay. Well, here, of course, I could pull this 2 out front. That's one of my favorite properties, pulling those constants out. And I know this integral. This was given to me. I was told that that was 7. So I've got 2 multiplied by 7 plus, well, this integral is pretty easy to do. We find the antiderivative, evaluate at 4 and 1. So 20 minus 5. So we can add 15. So we end up with 14 plus 15 for an answer of 29. And a quick review of finding the area between two curves. Okay, And again, I'm assuming you have seen this before in Calc 1. Finding the area between curves, we always, of course, do the integral of the top function minus the bottom function. Okay. So in our case, we get the integral. 3 minus x is on top. The parabola is on the bottom. If you didn't know that, there's a pretty easy way to check. Okay. And I'll show that to you real quick right now. Now I gave you a graph, but let's say you didn't have a graph and you needed to figure out the bounds. Well, you would want to know where these things intersect each other. So I would pull the x over. I would bring the 3 over by subtracting it. So what I have now, of course, everything on the left side is gone, so 0 equals x squared minus 3x and plus 0. Well, now I could do a little factoring. And I'm looking for where x multiplied by x minus 3 is 0. So x could either be 0 or 3. And you can see 0, x equals 0, x equals 3 are where the intersection points are. Those become our bounds. Okay. Now, if you, again, didn't have a graph, what I would do is plug an intermediate value, something between 0 and 3 into these two. Maybe evaluate at, I don't know, x equals 1. So you plug in 1, you say 1 minus 4 plus 3, and 3 minus 1, and you find out that the line gives you a larger value, so it must be the top function. Okay. At this point, we find the antiderivative. So 3x minus 1/2 x squared minus 1/3 x cubed plus 2x squared minus 3x. And we're evaluating at 3 and 0. Let me just make a note here. The antiderivative here is 1/3 x cubed, but there's this subtraction out front. The antiderivative here is negative 2x squared, but it's minus a negative. The antiderivative here is 3x, but minus a positive 3x. Okay. Now maybe you want to do a little simplifying first, like pointing out that the 3x's are going to be gone. Okay, we could also combine the 1/2 x squareds, but I'm not sure that that's necessarily going to be any easier at this point. So now we plug in 3. We get negative 9/2 minus 9 plus 18. And we plug in 0, we get 0. So again, let me just recap. We plug in 3, so 1/2 times 9, negative 1/2 times 9, minus 1/3 times 27, plus 2 times 9. Okay. So we end up here with negative 9/2 plus 9, which is the same as negative 9/2 plus 18/2, which is positive 9/2. And that is the area between these two curves. So you find the bounds by setting the two equal to each other. You figure out which one is on top, which one's on bottom, and remember it's always just going to be the top minus the bottom, the integral of the top minus the bottom. You find the antiderivative, you plug in the bounds, and then you calculate.